This is the third and final video lecture dealing with linear motion. In an earlier video or pair of videos we discussed linear horizontal motion. That involved objects moving along a straight track, a horizontal line. We call that line the x-axis. And I introduced a few equations, very important ones, dealing with linear horizontal motion. Here they are. The later velocity of an object equals its earlier velocity plus the amount of velocity gained or lost because of the acceleration of the object. A stands for the acceleration. A can be a positive number, in which case the velocity is becoming progressively more and more positive, or alternatively, less and less negative. A can be positive or negative. V bar is the average velocity of the moving object over some period of time. It's found using the middle value rule. First, find the sum of the beginning and later velocities and divide by 2. Alternatively, you could find the average velocity using this equation by twisting it around, but that's not usually what we do. We're not so much interested in that kind of activity. This equation can be used to find the displacement, called x, of an object over some period of time t. And we put to use the average velocity expression that we found earlier. An alternative way to find the displacement of an object is shown here if you're given the following numbers. If you know the initial velocity of the object and its acceleration, then all you have to do is specify a period of time called t that you're interested in and substitute that value of t into this equation. You'll find the future x coordinate of that object, which represents the displacement of that object. The final equation, which I did not derive, nor did I derive this, is shown here. The square of the later velocity equals the square of the earlier velocity plus 2 times the acceleration times the displacement. What a messy equation. Not a very pleasant one to deal with or to think about. Well, it's pleasant to use because it often will save you a lot of time in problems that otherwise require you to manipulate in a variety of ways the first 3 equations. Well, we discussed linear horizontal motion. Next we'll study linear vertical motion. But there's very little new in our coming study of linear vertical motion. The equations are virtually identical, except for a couple of minor changes. Let me show you what the new equations are and how they compare to the old ones. I've listed the old ones here for linear horizontal motion. The rule is this: wherever you see an x representing the x coordinate of a particle on the x-axis, an object on the x-axis, replace it with a y. That's the symbol we'll use to represent the y-coordinate or the vertical coordinate of an object moving vertically, either moving upward or downward or both, one after the other. Wherever you see an x in the first set, put a y. That occurs here, here, and there. The last change is simple. Wherever you see an acceleration a, there, and there, and there, replace it with negative g. Well, what is g? G is a symbol that stands for this very popular number, commonly used number, 9.8 meters per second squared. It's referred to as the acceleration caused by the pull of the Earth. Shorter form, the acceleration due to gravity. So wherever you see an A in the first list, put a negative g. And I did that here, replacing that A with a negative g. Nothing to do in this line. Replace that x with a y. Replace this x and that t with a y and a negative g, respectively. And finally, replace the a with negative g and the x. Well, what do we see here? Replace it with a y, not an x. But you knew that all along because you were reading ahead. All right, now let's work a simple problem involving vertical motion. The point I'd like to make is this. whatever skills you develop to solve a myriad of problems, dozens of them have been recommended, involving linear horizontal motion, those same exact skills and lines of thinking can be used directly to solve correspondingly similar problems dealing with objects rising or falling along a vertical straight line. Well, let's work the following problem. We have an object thrown or fired or otherwise propelled upward with an initial velocity of 80 meters per second. It rises straight up, and as it rises, the pull by Earth is slowing it down, pulling down on it. With each passing second, Earth eats away at the upward vertical velocity at the rate of 9.8 meters per second with each passing second. And so the object will eventually lose all of its vertical velocity, and for an instant it will be at rest, but just for an instant, then we'll start falling back down, just as if it were at that altitude, unknown, and dropped. Well, our goal is to know or determine how high that object went. What is its maximum height, the maximum altitude it reached? Altitude is measured relative to where the object once was, down here. So we seek the value of y when the velocity has been reduced to 0. Well, we'll use the last equation presented in this list, replacing the g with 9.8, substitute of 0 for v, 80 for v naught, and you can see the rest, solve that equation quite easily for y, the maximum height reached by this projectile. All of the problems that you may have already encountered, either in the notes or in the practice problem list or in the sample examination, you can translate into language that relates to vertical motion and then copy down whatever line of logic and equations you use to solve those problems, translate them into symbols that relate to vertical motion, and you'll arrive at the answer just as easily, or not so easily, as you did for those other problems. So the message is this: if you understand these equations here and how to work problems involving them, you'll have no trouble with vertical motion. That will do it for this video lecture. I'm sure you can't wait to see what's next.